engineers who build bridges must think about the distance to be covered, as well as the type of traffic that will cross the bridge. A bridge for cars and trains must be stronger than a simple bridge for just foot travel. Engineers must consider many things, like the distance to be spanned and the types of materials available, before determining the size, shape, and overall look of the bridge. Let's take a look at how forces like tension and compression act on these bridges. The beam bridge consists of a horizontal beam supported at each end by piers. The weight of the beam pushes straight down on the piers. The farther apart its piers, the weaker the beam becomes. This is why beam bridges rarely span more than 250 feet. The truss bridge consists of an assembly of triangles. Truss bridges are commonly made from a series of straight steel bars. Can you tell how tension and compression act on the truss bridge? The arch bridge's semicircular structure distributes compression through its entire form and diverts weight onto its abutments, which take on the pressure. The suspension bridge can span 2,000 to 7,000 feet. Way farther than any other type of bridge. Most suspension bridges have a truss system beneath the roadway to resist bending and twisting. What are the similarities and differences as to how tension and compression act on the following cable-stayed and cantilever bridges?
When was the last time you had to do this, or this, to get across a stream, river, fjord, or lava pit? Probably never, because we have these things called bridges. Bridges are awesome. But what are all these different types of bridges that you see around? Why don't they all look the same? Let's find out. Engineering. The most basic type of bridge is a beam bridge. It has the most simple design, with the beam, also called the bridge deck, that is supported at both ends. Let's drop into our diagram mode to see how the forces act upon this bridge. When a load is applied to these bridges, they bend and experience two types of forces. The top of the beam is pushed together, which is called compression. The bottom of the bridge is pulled apart, which is called tension. Here we are using lasers to build model bridges out of balsa wood and plywood. Always wear purple gloves while handling balsa wood. Safety first, kids. You can see the simple design. Now let's see what happens when we apply forces to it. To do this, we'll use a compression tester that can apply up to 20,000 pounds of force, although we probably won't get that high in this test. The compression tester will apply a load, or in other words, a weight, and measure the strain, which is how far the material moves in response to a load. Also to help us on this test will be these Lego people, who will measure the ability to be launched from a bridge when it breaks. Critical information for bridge designers. Officer.
Hello.
You see that as the load increases, the bridge bends, and eventually breaks at a load of 115 pounds. But now, what if you want to span a longer distance? Here we use the same deck material on top, but we have doubled the length of the bridge. This time, our main test subjects will be the happy farmer chef, hat man, bike guy with no helmet, shame on you. You can see that the longer bridge bends even more, and it breaks at a much lower load, only 25 pounds, which is 80% weaker than the short beam bridge. Plus, the LEGO people get launched into space. That isn't very good. We want the bridge to support a lot of weight over a long distance. So how can we make bridges that span longer distances? There are other bridge designs that allow us to use the same deck material and span longer distances. This takes us to the curviest of bridges, arch bridges. An arch is a great way to evenly distribute a load and has been used in bridge building for a long time. In this example, we just have a beam bridge with an arch underneath. The load is distributed through the arch into the ground. Notice how only compressive forces are present and no tension forces. This is great for wood and stone bridges because they are much stronger in compression than tension. In our model arch bridge, we use the same long bridge length with added arch supports on both sides. To help us is Tricycle Man, helmet, good job, classy businesswoman, and this crazy guy. Let's go! You can see that the beam does not bend as much with the arch underneath, and that reaches a higher load before it fails, 100 pounds, which is 500% stronger than the long beam bridge. Here we have seen that beam bridges get weaker as they get longer. Adding an arch makes the bridge very strong, but arches have length limitations. Beam and arch bridges historically have relied on wood and stone as building materials. These materials are usually only strong in compression and not in tension, which restricted the designs that could be used. However, with the discovery of steel, bridge builders now had the ability to add structural units that would be strong in tension. This led to more intricate styles of bridges that we will explore in our next video. In our last video, we looked at the simple designs of beam and arch bridges. Now let's move into the modern age with the truss bridge. Truss bridges make use of a large frame called a truss that sits on top or below the bridge deck. In this case, it is on top. While it may seem like we are only adding weight to the deck, the design of the truss distributes the load through the frame so that the deck does not experience as much of a load. Each segment of the truss experiences different loads of either tension or compression. We apply 2 equal loads to the deck and calculate the loads in each segment, which are shown as percentages of the total load. You can see that the largest loads are on the end and top segments, while the middle segments have none. Remember that when we do the compression test. Spoiler alert! Let's see if this convict gets shot out of his truss jail. So how do you think the truss will break? Discuss. Thanks for coming, Yoda. I love your work. As you can see, the outer segments of the truss are the first to break because they were handling the largest part of the load. The diagram showed that the outer and top segments had the same loads. Why didn't the top break? That's because the top pieces are aligned along the grain of the wood, and wood is stronger in that direction. Adding the truss allowed the same deck length to hold 32 pounds, which is 25% stronger than the beam bridge of the same length. The final type of bridge we'll discuss is the iconic suspension bridge. Although the only suspension bridge around us is less than iconic, but the same principles apply. Suspension bridges utilize thick steel cables that support the deck and transfer the load to the towers and to the anchors at the end of the bridge. Supporting cables are used to suspend the bridge deck from the main cables. The main cables and supporting cables of the bridge are always under tension. The cables transfer the load to the towers, which experience compression, and also to the anchors at the end of the bridge. In our model, we used wires for the main cables and supporting cables. Some of the construction is not ideal because it is difficult to simulate some of the joining points and anchors on a small scale. For this test, we need a full cast of characters. The Misfits versus the Bike Gang. Oh, there's Crazy Guy again. Classic Crazy Guy. As force is applied, the cables transfer the load out to the towers and anchor points at the end. This force distribution maintains the integrity of the deck so that even when it does break, it doesn't really launch anyone. Unfortunately, I really want to see the Crazy Guy get launched. This bridge supported 32 pounds, which is the same as the truss bridge. The truss and suspension bridges were stronger than the long beam bridge, but weaker than the arch bridge. This may have been unexpected, but the real advantage of truss and suspension bridges are that they can span longer distances than beam and arch bridges. Now what we've all been waiting for: crushing a Lego man.
The Michael Callahan Pat Tillman Memorial Bridge in Boulder City, Nevada, was built to reroute traffic on the 93 highway and reduce the number of hairpin turns and blind curves that drivers had to conquer to cross the Hoover Dam. It is an arch bridge that is 900 feet above the Colorado River. This is a 1907 historic railroad bridge located in Wadsworth, Nevada. Can you tell what type of bridge this is? This is the Galena Creek Bridge. It is a twin-span concrete arch bridge in Washoe County, and it carries Interstate 580 and US Route 395 over Galena Creek. This is between the cities of Carson City and Reno. Supposedly, this bridge is the largest cathedral arch bridge in the entire world.